Alright everyone, so welcome back to week 4. So we're into the second half of the course now. So I'm going to have two different topics that I'm going to do in this video. So the first one's going to be on logarithms, and the second one's going to be on what we'll call inverse functions. Okay, so when we talk about logarithms, we want to talk about first some arithmetic and algebraic rules for dealing with logarithms. So if we have the expression b to the x, so we have some base raised to the power of x, and we say that's equal to y, that's the equivalent of saying that x is the logarithm base b of y. And the special logarithm that we use has the base of e, so this was the number where e to the x is its own derivative, e to the x, we saw that a while ago. And e to the x equals y is the equivalent of saying x is the logarithm base e of y, or as it's more commonly known, the natural logarithm of y. One thing that I've learned in doing this is that Americans tend to pronounce that expression as ln of y, and everyone else in the world pronounces it as ln of y. Not sure why. Anyways. So remember that e to the minus x is 1 over e to the x. That's not minus e to the x or something else like that. If we have e to the x and then that's raised to the r, that is e to the x times r, which is different from the tower function e to the x and then raise that to the r. If we have bases raised to a power, we can add the powers. So e to the a times e to the b is e to the a plus b. And then the important ones for what we're going to do here are rules for logarithms. So if we have the natural logarithm of x times y, we can rewrite that as ln x plus ln y. If we have the natural logarithm of 1 over x, that's minus the natural logarithm of x. And then if we have the natural logarithm of x divided by y, that'll just be ln x minus ln y. But then if we have the natural logarithm of x raised to the r, so it's x raised to the r and then we take the natural logarithm of that, we can pull the exponent r out in front and get r times the natural logarithm of y, and that is different from taking the natural logarithm of x and then raising that whole expression to the r. So those two things are very different. You want to keep those, you want to keep straight which ones you're doing. Okay, and well, we're interested in derivatives, so we should state what the derivative is for natural logarithm of x, and that is going to be 1 over x, and it's also the derivative of natural logarithm of absolute value of x. Okay, so we want to go through and do some examples. So the first one that we'll do is the natural logarithm of 3x. So here we have a chain rule. Our outer function is going to be ln x, our inner function is going to be 3x. So the derivative of our outer function will be 1 over x, derivative of our inner function will be 3. So that tells us that the derivative of ln of 3x is going to be f prime of g times g prime, or 1 over 3x times 3, which gives us 1 over x. If we take the derivative of x times ln x, we'll have a product rule, where our first function will be x, our second one is ln x. The derivative of our f is going to be 1, derivative of g prime will be 1 over x. So from our product rule, we'll wind up in the end with ln x plus 1. If we want to find the derivative of the natural logarithm of cosine of x, we'll have a chain rule here, where our outer function is going to be ln x, our inner function is going to be cosine. So the derivative of our outer function is going to be 1 over x, and the derivative of the inner function is going to be minus sine of x. So from our chain rule, we'll get 1 over cosine of x times minus sine of x. So we have minus sine over cosine, but remember that sine divided by cosine is tangent. So it tells us that the derivative of natural logarithm of cosine is going to be minus tangent. Okay, so the fourth example that we have here, it might seem strange why I would put this one in with logarithms, but it should be clear what we're going to do in just a moment. So we want to find the derivative of x plus 1 times x plus 2 times x plus 3 all divided by x plus 4. Now we could do this some combination of the product rule, quotient rule, maybe expand out the numerator and then just do a quotient rule, something like that. But I'm going to propose that that logarithms can help us a lot here. So the first thing we're going to do is we're going to take y to be x plus 1 times x plus 2 times x plus 3, I'll divide by x plus 4, and then we're going to take the natural logarithm of both sides. And when we do that, we'll go and use the rules that we just had for dealing with logarithms. So the first one that we'll have is we'll get the natural logarithm of x plus 1 times x plus 2 times x plus 3, and then subtract off the natural logarithm of x plus 4, and then we'll use that product rule that we just had for natural logarithms to say that the natural logarithm of y is the natural logarithm of x plus 1 times the natural logarithm of x plus 2 times the natural log... Then we can say that the natural logarithm of y is the natural logarithm of x plus 1 plus the natural logarithm of x plus 2 plus the natural logarithm of x plus 3 minus the natural logarithm of x plus 4. And from there, we're going to go and use what we did last time and take implicit derivatives. So we'll just assume that y is some mystery function of x, take derivatives of both sides. When we do that on the right, what we've done is switch products and quotients into just sums, or sums and differences here. So we'll find the derivative of the natural logarithm of x plus 1. Well, we'd easily find that to be 1 over the argument times the derivative of the argument, just using our chain rule. So we'll get 1 over x plus 1 times the derivative of x plus 1, which is just nicely 1. Well, then the derivative of the natural logarithm of x plus 2 is just going to be 1 over x plus 2. The derivative ln of x plus 3 is 1 over x plus 3. And the derivative of ln of x plus 4 is 1 over x plus 4. Then we'll come back to the derivative on the left-hand side. So we're looking to find the derivative with respect to x of ln y. Well, from our chain rule, we'll get 1 over y times dy by dx. And remember here, the thing we're trying to find is dy by dx. So then all we'll do is we'll just multiply both sides by y. The exact same methodologies we used last time when doing implicit derivatives, isolate for the dy by dx. So we get dy by dx is equal to y times our 1 over x plus 1 plus 1 over x plus 2 and so on. And then as we'd said last time, it's good form to just go and put back the original expression for y. So we'll get our dy by dx given here with this 8th line. Kind of a long expression, but that's what we'd wind up with for a derivative. And if you're really, really interested, you could go through and do the same problem again using product rule, quotient rule, whatever. You'd get the same answer, but I think you would do a lot more work, be less straightforward. Okay, so let's go and do a few more examples. So we'll do a couple of kind of different looking things with exponents. So we'll first go and find the derivative of b to the x, where b is going to be some constant. Okay, so with these kind of equations, or these kind of functions, the rule of thumb is that whenever you see an x that is sitting in the exponent, and it's not something like e to the x or e to some function of x, you have to use logarithms to get the function down, or I guess you could remember maybe specialish looking things, but it's just much simpler to start off and use logarithms as we're going to do here. Also, it means you don't have to remember kind of obscure derivative rules as well, which I guess is good. Okay, so we'll say that y is going to be b to the x, and we'll take natural logarithms of both sides. So we'll say that the natural logarithm of y is the natural logarithm of b to the x, and using that power rule for logarithms, that's the same thing as x times ln of b. Now what we'll do is just take the derivative of both sides with respect to x. So on the left-hand side, we get our d by dx of ln y, and on the right-hand side, we get d by dx of x ln b, which is just going to be the natural logarithm of b, because ln b is a constant. Okay, so now we'll isolate for the dy by dx, knowing that our derivative on the left will be 1 over y dy by dx, and that'll give us dy by dx is ln b times y, and y we said is b to the x, so our derivative here is going to be the natural logarithm of b times b to the x. Okay, so now let's go ahead and find the derivative of the logarithm base b of x. Well, we'll do the same kind of thing. We'll first start off by saying that y is equal to the logarithm base b of x. But we could translate this from what we said at the beginning about logarithms to say that x is b to the y. Now, we just found the derivative of b to the x, and we're now going to find the derivative of b to y, where y is assumed to be some function of x. So when we take our derivatives with respect to x of both sides, we'll see that on the right-hand side we just get 1, we have dx by dx, and on the left-hand side we have a chain rule. So we're trying to find the derivative of b to the y of x. So we have a function of x, or a function composition here. Our outer function will be b to the x. Our inner function will be g of x equals y of x. From what we just said, the derivative for f will be ln b times b to the x, and g prime will be dy by dx. So our derivative with respect to x of b to the y will be the natural logarithm of b times b to the y times dy by dx, and then from what we just said, that's all equal to 1. So in other words, our dy by dx is going to be 1 over the natural logarithm of b times b to the y, but y is the logarithm base b of x, and those two operations will undo each other, so taking b to the logarithm base b of, in this case, x, will just give you back x. In the same way that taking e to the natural logarithm of x will give you just back x. Those are inverse operations. They nicely undo each other. So we get that dy by dx is going to be 1 over the logarithm, natural logarithm of b times x. Okay, well, how about the derivative of x to the x? So we'll again start off by saying that y is equal to x to the x, and we'll take natural logarithms of both sides. So we get that the natural logarithm of y is the natural logarithm of x to the x, which is x times the natural logarithm of x. Conveniently, we just found that the derivative of x ln x was ln of x plus 1. So we'll get that dy by dx is going to be y times ln of x plus 1, which is x to the x times the natural logarithm of x plus 1. Okay, so there's one other thing that I should point out here. And in the past, what I've seen a lot of people do is they see you have x raised to something, and for no apparent reason, go and invoke the power rule. Remember that the power rule only works when this exponent is a constant. So what a lot of people would do is they would say, well, I've got an x that's in my exponent, I'm going to multiply that out in front and then subtract 1 from the power. So you would get x times x to the power of x minus 1. But if you went through and you simplified that out, you would see that that's just x to the x again. But interestingly, if we come down to this final answer, what we see is there is an x to the x here. If we were to go and expand this out, we'd get x to the x times natural logarithm of x plus an x to the x. So what you'd wind up with is something that's kind of similar to the power rule plus extra stuff. And if just at the beginning you'd blindly applied the power rule, you'd be missing the extra part, which would be this x to the x natural logarithm of x. So remember, power rule only applies when your exponent is a number and your base is x. It doesn't apply when it's x to some function of x. Okay, next example. We'll find the derivative of 1 over x raised to the power of natural logarithm of x. When we do that, when we do the same steps as before, we'll take y to be this expression, take natural logarithm of both sides, and when we simplify things a little bit, we get that the natural logarithm of y is minus the natural logarithm of x squared. And the 2 is outside of it's outside of the natural logarithm. This is also why I advise putting parentheses around things so it's clear whether the 2 is inside the natural logarithm, whether it's outside, because it clearly matters. Okay, so now we'll go and take the derivatives of both sides. On our right-hand side, we'll have a chain rule, so we have the natural logarithm of x and it's all squared. So our outer function will be x squared, our inner function will be ln x. So the derivative of f will be 2x, the derivative of the inside function will be 1 over x. And that tells us that the derivative of ln of x all squared is going to be 2 ln x times 1 over x. Okay, well, we know that our derivative of ln y with respect to x is 1 over y dy by dx, and that's equal to minus 2 ln x times 1 over x. So dy by dx is going to be minus 2 ln x times 1 over x, and when we put back the original expression for y, we'll wind up with minus 2 times natural logarithm of x, all divided by x to the natural logarithm of x plus 1 power. So kind of a mess, but we can find it with not too bad of a procedure. Okay, so then two more. I don't know, I guess these are getting progressively worse. So we'll take x to the power of cosine of x, and we'll do what we've typically done at this point. We'll say y is x to the cosine of x, take the natural logarithm of both sides. So we get the natural logarithm of y is cosine of x times natural logarithm of x. And we want to go and take derivatives of both sides, so our left-hand side at this point should be pretty standard, 1 over y dy by dx. And our expression on the right-hand side will just have a product rule, so we'll have natural logarithm of x times the derivative of cosine, plus cosine times the derivative of natural logarithm of x. And when we go and isolate for dy by dx, we get y times minus ln x sine of x plus cosine of x divided by x. So we get a final answer of dy by dx is x to the cosine of x times cosine over x minus ln x sine x. Okay, and then the last one that we're going to do is x to the power of x cosine of x. So we'll say that y is x to the x cosine of x, and ln of y is x cosine of x ln of x. And we have some options here. So one is we could go and do the product rule on the right-hand side, so we'd have 3 different functions. We could totally do that. I think in general it's easier to go and use logarithms whenever you have to do 3 products or 2 products and a quotient rule, but that's just me. You can do it however you like. So we'll take the natural logarithm of both sides again. So now on the left-hand side we'll get ln of y, and on the right-hand side we'll get ln of x cos ln x. So using what we know about products and logarithms, ln of x plus ln of cosine plus ln of x. Okay, so on the right-hand side, we have the derivative of ln of x. Well, we know that that one is 1 over x. We have the derivative then of ln cosine of x, and a few problems ago we found that that's minus tangent of x. And then we have the derivative of natural logarithm of x. Well, we know from what we'd have with the chain rule and natural logarithms, the derivative of ln of x is going to be 1 over ln of x times the derivative of ln of x. So in other words, on the right-hand side, we'd get 1 over x minus tan of x plus 1 over ln of x, 1 over x. Okay, so now let's come back to the left-hand side. So we need to find the derivative of ln of y. And we could do this in a few different ways. What I'm going to do is I'm going to say our outer function is ln of x, and the reason for that is we just found its derivative on the right-hand side, and then our inner function is y of x. So from what we just found on the right-hand side, the derivative of ln of x is 1 over x ln x, and then our g prime is just dy by dx. So the derivative of ln of y with respect to x is going to be 1 over y ln of y times dy by dx. And now we'll bring the left and the right-hand side back together. So on the left-hand side, we'll get 1 over y ln y dy by dx, and that's going to be equal to 1 over x minus tan of x plus 1 over x ln x. And now we just want to isolate on the left-hand side for the dy by dx, so we'll multiply both left and right side by y ln y. Okay, well, from what we've said before, y is x cosine x to the x cosine of x, and ln of y is x cosine of ln of x. So just putting those two things into line 13, we'll get a final answer of dy by dx is going to be equal to x to the x cosine of x times cosine of x times ln of x, and then all times 1 over x minus tan of x plus 1 over x ln x. Okay, so that covers the first half of what I want to do here, which is look at logarithms. Okay, now we want to give kind of just a brief talk about inverse functions. So first we need to talk about when inverse functions actually exist and what they are. So we'll say that a function is one-to-one if whenever you have the output is the same, so you're given 2 points x1 and x2, and you're told that f of x1 is f of x2, that necessitates, so it's always the case, that x1 and x2 are the same thing. So in other words, what it says is that every input gets mapped to a unique output. One way you could think about this is jersey numbers on... so you want to be careful with this, because college football teams, you'll have players get mapped to the same number. So I'll say NHL teams. At any one point on an NHL team, if you're told that that on the current roster, there's somebody, you have one person that's number 13, and you have another person that's number 13, you're talking about the same person. That's kind of the idea, is jersey numbers map players to jersey numbers, and every player gets mapped to a unique jersey number, and the reverse. Every jersey number is talking about a unique player. Okay, so if you're given a one-to-one function, that function f has an inverse function which we'll call f to the minus 1, and f inverse of x, so f to the minus 1 of x, is the unique number y, so that f of y is equal to x. One thing that I should clarify here is that when we're using f to the minus 1 in this context to talk about inverse functions, we're not talking about 1 over f. We're talking about the inverse, which is kind of different. Okay, so one property that we have is, so long as the inverse function exists, f of f inverse of x and f inverse of f of x is x. So they undo each other. So in one sense, it's like multiplying by 3 and dividing by 3. You get back what you started with. Okay, so suppose that we're looking at sine of x here. Well, sine of x, it's going to keep oscillating up between minus 1 and 1, and this would be a problem for getting an inverse function over all real numbers. So for example, we could get that sine of 0 is 0, but sine of minus pi is 0, sine of plus pi is 0. That's a problem because what we want is every value, every output to have a unique input. In this case, you would have the output 0 has minus pi, 0, pi, and so on as inputs. What we could do is limit the domain that we're going to consider. So if we limit things to looking between minus pi over 2 and pi over 2, what we'd see is that every value in between minus 1 and 1 on that interval has a unique input. So another way to think about this from maybe high school algebra or something is, for a relation to be a function, it has to pass the vertical line test. For something to be an inverse function, it has to pass the horizontal line test. And if we limit things to looking between minus pi over 2 and pi over 2, we would see that sine will pass the horizontal line test there. Okay, so let's go and get some derivatives for inverse functions. So for inverse functions, I'm going to primarily stick to writing arcsine, arccosine, arctangent, just to make it clear that I'm not talking about 1 over sine, 1 over cosine, 1 over tangent, and so on. Okay, so I have what the derivatives are listed at, and let's go and see why those are actually the case. So let's start off by saying that sine of y is equal to x, and to do this we'll go and look at some triangles. So I have this triangle here, and this angle that I've got listed here is going to be y, and we're saying that the sine of y is x. So that allows us to go and fill in parts, side lengths of the triangle. So we'll say that our opposite side is x, our hypotenuse is 1, and then that means that the adjacent side has to be square root of 1 minus x squared. Okay, so then the next thing that we could do is we could say, well, if sine of y is x, equivalently we're saying that y is the arc sine of x. Well, let's go and take the derivative of both sides here. So we'll take the derivative of sine of y, and we'll on the left-hand side, and then we'll have the derivative of x with respect to x on the right-hand side. So more implicit derivatives. On the right-hand side, we just get 1, and on the left-hand side, from implicit differentiation, we'll get cosine of y times dy by dx. And then isolating for dy by dx, we get 1 over cosine of y. And from what we would have here, cosine of y, we'd get our adjacent divided by our hypotenuse. So we'll get 1 over the square root of 1 minus x squared. And we could do the same kind of trick to get cosine of x as well, and also tangent, but I'll do the tangent one as well. So suppose that tangent of y is x. That tells us that our opposite side is going to be x, our adjacent side is 1, so our hypotenuse is the square root of 1 plus x squared. Doing the same kind of thing from before, we'll have that the tangent of y is x, and we'll use this to come up with the derivative for arctan. So y is arctan, and if we want the derivative of arctan, we're trying to find dy by dx. So we'll do implicit differentiation to get that one. On the right-hand side, we'll again have dx by dx, which will give us 1. And on the left-hand side, we'll use implicit derivatives on tangent of y. Well, the derivative of tangent is secant squared, so we'll get on the left-hand side secant square of y times dy by dx. And then isolating for dy by dx, we'll get 1 over secant squared, or cosine squared of y. And from what we have drawn here with the triangle, our adjacent side is 1, our hypotenuse is square root of 1 plus x squared, and we're squaring the whole thing, so we get 1 over 1 plus x squared, which is exactly what we wanted to find. Okay, so one more example to wrap this up. So let's go and find the derivative of arcsine of x over a for some non-zero constant a. Well, here we have a chain rule. So our f, our outer function, is going to be arcsine, so the derivative of that will be 1 over the square root of 1 minus x squared, and our inside function is going to be x over a, or the derivative will be 1 over a. So from our chain rule, we'll get that the derivative of arcsine of x over a is going to be 1 over the square root of 1 minus x over a, and that quantity is squared, times 1 over a. And when we simplify things down a bit, we get that the derivative will be 1 over the square root of a squared minus x squared. So I remember there was one question, I think, on tests a couple of years ago, and the problem was very similar to this. You had saying like arcsine of x over 4. A lot of people forgot to do the chain rule to get that derivative, and they got a wildly wrong answer. So again, whenever you have some kind of function composition, so you're looking at something that you don't have a direct rule for, just remember to use your chain rule. Okay, so then the second problem was we wanted to look at the arcsine of sine of x, and we want to go and find and also simplify f prime of x. Okay, so we want to find the derivative of f, so we have a function composition here, so let's go ahead and use our chain rule. And I'll explain why we're doing this in just a moment. So the first thing that we'd have is our outer function is arcsine, derivative is 1 over square root of 1 minus x squared. Our inner function is sine of x, so our derivative of that is cosine. So from our chain rule, we'll get 1 over the square root of 1 minus sine squared of x times cosine, but 1 minus sine squared is cosine squared, and we're taking the square root of that, so we'll get cosine divided by the absolute value of cosine. Okay, so one thing we might ask is, well, we just said that sine and arcsine are inverses of each other. And that's true. But one thing that we should remember is that whenever you put in x to sine, so you put in some angle, you get out a value in between -1 and 1 all the time. When you put in a value between -1 and 1 into arcsine, you're going to get out a number in between minus pi over 2 and pi over 2. So if you just said, well, arcsine of sine of x is always x everywhere, sort of. You get that, but everything gets smashed back into being in the interval of minus pi over 2 to pi over 2. And we'll see how this matters in a moment. Okay, so we've said that our derivative for f is cosine divided by absolute value of cosine. Well, so what does that mean? Well, it means that if cosine is positive, absolute value of cosine is just cosine. So you get cosine divided by cosine, which is 1. In the event that cosine is negative, the absolute value of cosine is minus cosine. So you have cosine divided by minus cosine, which is going to be minus 1. Well, then there's the third possibility, and that's that cosine is 0. So something like pi over 2, minus pi over 2, and so on. So in those places where cosine is 0, you'd have that f prime is 0 over 0, so it is undefined. So in the places where cosine is 0, the function does not exist. Okay, so what happens if we plot this function? Well, what we said is that in between minus pi over 2 and pi over 2, you would just get back x. So that would be the what we'd maybe expect. We get that arcsine of sine of x is just going to be x in between minus pi over 2 and pi over 2. As we go away from that, though, what we'd see is that when we move from the first quadrant, so where we're looking between 0 and pi over 2, going between pi over 2 and 3 pi over 2, we'd said that our derivative is minus 1, so we're just going to get a line of slope minus 1. And as we get back into the fourth quadrant, we'd have a line of slope 1 and so on. And what we'd see is that all of these points where cosine is 0, so pi over 2, minus pi over 2, minus 3 pi over 2, 3 pi over 2, we have that sharp turn, a corner, a cusp, depending upon the terminology you want to use. And in all of those places, the derivative doesn't exist, and that's what we see from this plot. So this is what's referred to as just a sawtooth kind of plot, because if you take a saw, the plot kind of looks like all of the teeth on the saw. Okay, so that tells us about arcsine of sine of x. What about sine of arcsine of x? Well, the thing to remember here is that arcsine of x is only defined for values in between minus 1 and 1. Because remember that arcsine of x is saying the output you get from arcsine of x is saying what number or what angle in the range of minus pi over 2 to pi over 2 has the sign of the given value. So if you wanted to find arcsine of 2, what you would be asking for is to get an angle in between minus pi over 2 and pi over 2 so that the sign of the angle is 2. Well, no such value exists. So arcsine of x is only defined for values in between minus 1 and 1, so that way an angle exists with the prescribed sign value. So g of x is only defined for minus 1 to 1, and for those values, g of x is x. But it doesn't exist for any x value outside, so bigger than 1 or less than minus 1. Okay, so that gives us what we want to see about inverse functions and also derivatives with logarithms. And I will put a worksheet up in Wild Courses, and I'll see you all in the next video.